In this future world, there is only one vast ocean stretching 20,000 kilometers across. This global ocean has come about because the slow drift of the continents has brought them all together, creating one supercontinent surrounded by one global ocean. It's not just the planet that looks strange and new. This vast ocean is swarming with new life. Unfamiliar life. These are silver swimmers, shoaling where you'd expect to see familiar creatures like fish. So where are all the fish? What happened to them?
Every once in a while, the biology of the world is punctuated by a terrible event, often external, sometimes erupting from underneath the seas. Those terrible environmental events wipe out 80%, 90%, 95% of the species in the world, and they're called mass extinctions.
100 million years earlier, a dramatic increase in volcanic eruptions spelled disaster for the whole planet. Poisonous gases polluted the atmosphere and the oceans. Ash and dust thrown high into the sky blotted out sunlight for months on end.
If one of the consequences of a massive volcanic eruption is that the light goes off, the dust and ash in the atmosphere keeps sunlight from hitting the Earth, what will happen in the ocean? Well, the ocean is a soup of small, single-celled plants that live their lives very fast. You shut off the light for a day, that's a generation of these plants. Shut it off for a month, it's 30 generations. The ecosystem can collapse very quickly in that sort of setting because these organisms live very quickly.
Life in the ocean was in danger of total extinction.
In that situation, then, lack of sunlight can make a huge difference to the productivity in the whole biosphere. Mass extinctions show that many, many, many marine species go extinct all at once, even large groups that are very diverse.
And such an extreme mass extinction could even annihilate the most well-known group in the ocean, the fish.
Could they go extinct? They could go extinct in a mass extinction. What would the sea look like without them? What would the sea look like without fish?
The oceans wouldn't remain empty for long.
A sea without fish, it sounds unthinkable, but in fact, it could happen. But what would the consequence of that be? There would be many places in the sea when the sunlight came back that used to have fish and don't now. Would other organisms evolve to fill those ecological spaces? Probably they would, and there would be a huge number of different organisms poised, ready to take advantage of the demise of the fish.
The gap was filled by silver swimmers. But however strange they look, this design is around today.
If you go out in the sea now and you haul a plankton net through it, what you get is a wide variety, a very diverse set of tiny crustaceans, the larval forms of many shrimp and crabs and lobsters whose adults live on the bottom.
These larvae are tiny, smaller than grains of salt, but millions and millions of them drift in the ocean currents. And some of these crab larvae develop new ways to survive and flourish.
But suppose some of them actually began to reproduce in the plankton. Now this happens actually often in evolution, where a larval or a juvenile form develops the ability to reproduce in that form without having to turn into the adult. And by so doing, it seems like a whole new life form is created, in this case the silver swimmers.
With no fish in the oceans to eat them, silver swimmers could grow much bigger and evolve to fill all the niches left by fish. Some live in the open ocean, others on the seabed. Some are predators, some are scavengers. And this silver swimmer lives by filter feeding in surface waters that are once more alive with plankton. "200 million years from now, this is the most abundant creature in the sea." But evolution doesn't work in isolation. These uncountable numbers of silver swimmers are part of a new food chain in the global ocean. These weird flying creatures are flish, and they eat silver swimmers, swooping over the ocean in place of birds.
Flish look at first sight a little like birds. They're brightly coloured, they flap their wings in rather similar ways, but they've evolved completely separately from a very different ancestor. Flish, as their name suggests, have evolved from fish.
So fish did survive the mass extinction. They took the place of birds. But a fish that can breathe in air and fly?
In vertebrate animals, flights evolved at least 3 times. In every case, flights appeared by using the forelimb, exactly the same bones of our arm. But the way they've done it, the way the anatomies varied between the different groups, is quite different. In every case, it's the same end result. You need a large surface, which you can move and control, which you use to fly. We know that birds evolved from dinosaurs, and that the dinosaurs which were closest to birds were fast-running bipedal predators. It's been argued that birds might have jumped from trees, but I think it's much more likely that, like the dinosaurs, they ran on the ground, but jumped and held the wings out for balance and then to glide. Now in bats, the other living group of flying vertebrates, is much clearer. Bats jumped from trees. We have many animals today, like flying phalangers in Australia, flying squirrels in North America, which glide. They're very effective, but they can't really fly because they can't move the wing. But it's easy to see how that starting point of having a membrane stretched between the hands and the feet could evolve to become the wings of the bat. All of the animals have used these bones, the upper arm of the humerus, the lower arm, the ulna and the radius, and then the bones of the hand. In birds, most of the hand has disappeared. There are just 2 fingers fused together. In bats, it's all 5 fingers. The fingers are spread, skin goes across between the tips of them, and that forms the wing. The pectoral fin, the forefin of a fish, is exactly the same structure as the arm of a human or of my birds and bats. But the anatomy is very different. What will have happened in the fish is the basal bones have become longer, the joint has moved out away from the body, so the wing's articulated, it can change shape when it flies, and the fins have become stronger, and they're strengthening the whole wing, which produces the aerodynamic force.
As well as fins that turned into wings, another clue to the ancestors of fish is the way they feed. Snatching up silver swimmers on the wing needs a mouth that can extend and grab. That's something a fish jaw is well designed to do. Fish like the John Dory use their extendable jaws to suck up prey. So fish seem to have it made, soaring over an ocean stuffed with food. But even they are part of the new food chain. Sharp-eyed fish can see the silver swimmers from high overhead, big shoals of them glittering just below the surface. But this isn't a shoal of silver swimmers. It's a trap. The silver swimmer image was a pattern of light and dark playing over the body of a huge 25-meter rainbow squid. The squid's control of its body patterns is so sophisticated that from below it mimics the color of the water surface. Even a large silver swimmer rising up from the deep just blunders into it. But if the silver swimmer comes too close, the rainbow squid changes again, creating a spectacular flashing display. Even today, all squid and octopus, cephalopods, can do this, using tiny structures in their skin called chromatophores.
The chromatophores are a unique cephalopod invention. These are muscular organs in the skin, and they're little sacs that contain pigment. They can open and close. And when they're open, you can see the color spot. When they're closed, you can't. There's 3 colors, but different colors can be mixed in individual chromatophores. So you have a huge palette of colors available. And the most amazing thing is that each of those chromatophores is commanded by a nerve or several nerves maybe from the brain. So the brain is putting out all this patterning information. The chromatophores are responding because they're muscles. It's a motor control problem, just like walking, talking, moving my hands for me.
It takes millions and millions of color spots to create a display, and each and every one is controlled individually by the brain. That means a very large and complex brain. And that suggests squid are intelligent.
Today's squids are incredibly intelligent. There's no doubt about that. All the cephalopods living today are probably highly intelligent, judged by their brain-to-body size, which is a rough indicator of intelligence when comparing different types of animals. Squid is sort of on the level of a bird, way higher than fish, for example. Behaviorally, they show great signs of intelligence. They make these marvelous chromatophore displays with their skin coloration and pattern.
If squid are intelligent now, what could another 200 million years of evolution achieve?
200 million years from now, if the squid tendency to evolve its nervous system centralized nervous system continues the way it has been, these animals will be awesome.
Rainbow squid have a powerful brain. So powerful, they use chromatophores to make video displays. Vivid patterns of light and color all over their bodies.
They can use this to fool prey items into luring them in close. They can communicate with other squid in ways that are much more sophisticated than the way squid do it today.
The rainbow squid are so sophisticated, they can even imitate a big shoal of thousands of silver swimmers just below the surface. So food just flies into the squid's waiting arms. But feeding is only one of life's essentials.
Squid have a universal problem like all animals. That is, they need to find and attract a mate. Now, in the case of California squid, there's two important factors behind that. The first is that they have special spawning sites. The squid will, year after year, assemble by the millions on certain traditional spawning grounds, and that's where they'll mate. We don't know what brings them there or by what mechanism they get there. When they are on the spawning grounds mating, there's a lot of complex behavior associated with partner choice and securing a mate. It involves a lot of physical behavior, wrestling, fighting, things like that. It also involves body posture and chromatophore displays. In the California squid, there's a dramatic change in the coloration of the male at a certain part in the mating ritual where he turns his arms bright red. We don't completely know the meaning, but this is a very dramatic behavior. And in the case of the California squid, they only live 1 year, so after spawning, they die. The squid of the future will solve these problems much like the squid today, but in much more intellectual ways because they've been evolving their brains for a much longer time. They'll still come to certain spots for spawning, say a big seamount. Once there has to be meeting of the sexes and attraction of the most fit partners to reproduce.
Their courtship, previously a once-in-a-lifetime experience, is now an annual competition in light.
It could become a contest almost between different individual squids as to who could be the most flamboyant, is the only word I can think of as a display.
But being preoccupied with sex is dangerous. You're vulnerable. So rainbow squid gather to mate in the shallow water over seamounts, underwater hills.
If you get very big, one of the ways that you can protect yourself is to spawn in shallow water because your predators can't get in there. If you can get into shallow water and your predators can't, then in fact, that's a very good place to spawn. In this future world, the squid have moved into the shallow water in order to leave their predators behind.
But in the water over the great ocean deeps, even these huge squid are in trouble. For there are sharks that survived the mass extinction in the deep sea. Sharkopaths have become more chilling than ever. These killing machines now hunt in packs. In today's seas, sharks often congregate in big shoals, but they don't often hunt together. Each shark is bristling with sense organs that help it find its food. Their heads are covered in thousands of small pits, that can detect pressure changes and electrical discharges. Their nasal passages are lined with cells that pick up the faintest trace of scent. "200 million years in the future, sharkopaths are even more deadly predators, patrolling the oceans in carefully spaced arrays, signaling to each other in a code of flashing lights.
Sharks are magnificent creatures in today's seas, and they've survived mass extinctions in the past. And in the future, they survive as well. And they bring with them all the talents they have today, including a magnificent ability to sense the environment.
The ridges on the sharkopath's head are packed with organs that sense the slightest trace of their prey's scent. When a sharkopath detects something, luminescent patches on its sides start to flash, and they flash more quickly as the signal gets stronger. In this way, these future sharks can coordinate their attack.
In our future ocean, sharks hunt through the sea in arrays, searching for some scent, some sound, some signal of the rainbow squid that are somewhere in this enormous sea. And when one of them in these arrays catches a faint glimmer of a signal and turns toward it, all the rest do. They follow that signal, changing direction and time, honing in on it until finally the whole group of them finds this large animal.
The rainbow squid tries to camouflage itself, turning blue, making itself invisible. But as sharkopaths get closer, another sense kicks in. They can detect the electrical activity in the huge squid's nervous system. The squid panics, and its camouflage breaks down. Being smart isn't always an advantage. The huge, gentle rainbow squid can't defend itself against the simple brute force of nature's great killers. 200 million years in the future, and it's a new kind of world. The birds have gone, and so have the fish of the surface waters. In their place are flish and silver swimmers. Giant squid attack flish and are attacked by sharks. Life moves to the same evolutionary rules: eat or be eaten.